Circle geometry, rider number 3. We're going to go through this every time with this set of videos on riders, just to keep reminding of a process. The process from this video at that address, and here's a summary of it when doing geometric riders and proofs. First, you need to know the theorems. You need to be able to recognize them. Secondly, don't wait for the geometry to come to you. You have to ask yourself relevant questions. Start with what you're finding or proving. So don't just write everything you can see equal on a figure. It can be very confusing. If proving two angles equal, take one and find what it is equal to or combines with. And if proving something about lines or shapes, ask whatever it is so. So here's the rider number 3. A circle, tangent, PQ, PS parallel to QT, and RS equals TW. First, prove that KQ is a tangent to circle LQW. So we say, well, this is about a shape and lines, so therefore we say, what if it is so? So there's the situation. That would be a tangent to the circle through these 3 points. And if it was so, then the angle between the tangent and chord would equal to the interior angle subtended by the chord. The angle subtended the alternate segment. So Q2 would have to equal W1. So as I always say, so prove this. So now we're proving two angles equal. So we're going to go into the strategy now. When proving two angles equal, take one. So what is W1 equal to? Well, it's equal to S, angles in the same segment. Now we ask the question, is Q2 equal to S? Because remember, we're trying to prove Q2 equal to W1. And the answer is yes. They're alternate angles with the parallel lines. And therefore we have the two angles we need equal. So, going into the proof. W1 equals S. Angles in same segment. S equals Q2. Alternate angles, PS parallel to QT. Remember, it's always very important that you need to state the parallel lines, because angles can be alternate without the lines being parallel. 3, therefore, W1 equals Q2. Notice no reason. This is what we call axiomatic. It's an obvious fact that follows on. W equals S, which equals Q, therefore W equals Q. So therefore, KQ is tangent to circle LQW, and our reason is converse tan chord, or converse alternate segment theorem, or converse angle in the alternate segment. The next part, prove R1 equals L3. Prove R1 there equals L3 there. Now, I'm going straight to know the theorems, because I notice we have two lines equal to one another there. And as I said before, it can be a bad idea to fill in everything equal. Have a look at that figure there. Very confusing rather than helping, right? And I could even fill in more equal angles in there. But there's certain things, there are some theorems where it may be advisable. For example, if you have an angle in a semicircle, if you have a diameter, if, for example, SQ is a diameter, I would actually put that as a right angle, just so I don't forget it later. I would put that as a right angle between the diameter and the tangent. But of course, that's not a diameter, so we won't now. There's one. Angles subtended by equal chords, or angles in equal segments. Have a look. Chord, equal. It's sort of like angles in same segment, except one part of it has been shifted to another part of the figure. Those are equal. Therefore, they subtend equal angles there and there. So let's keep that in mind. All right, so now we're going to prove R1 equals L3. So we say, well, what is L1 equal to? L3, sorry. What is L3 equal to? Well, it's equal to R3, corresponding angles, parallel lines, and it's equal to W1 plus Q1. Now, I like this one because it already involves an equal angle there. So I'm going to go in this direction. So we say, well, what is R1 equal to? And straight away, I'm going to go a similar way by exterior angle triangle, because have a look. This is equal to that plus that, and that involves the other equal angle. So now we have W1 plus Q1 for L3, S plus Q3 for R1, and those two are equal. So all I have to prove is that W1 equals S to prove what we're expected to. So I say, well, is W1 equal to S? If not, then I'd start by saying, well, what is W1 equal to? But have a look at the diagram. There's the big hint in green. Yes, angles in same segment. So let's go about the proof. R1 equals Q3 plus S. R1 equals Q3 plus S. L3 equals Q1 plus W1. But Q3 equals Q1, angles subtended by equal chords, or angles in equal segments. And S equals W1, angles in same segment. Therefore, R1 is equal to L3. Proven. Let's go on to the next one. These often come up, and I love it when these come up because it's always fairly straightforward. PRKQ is a cyclic quadrilateral. So there we are. We have to prove that that's a cyclic quadrilateral. Our options open to us? Well, there are three converses. The first is the converse of opposite angle cyclic quads. So if we could prove a pair of opposite angles adds up to 180, is supplementary, it makes it cyclic. That's usually more difficult unless you let an angle be x and work it that way. Or we could prove the exterior angle. So this exterior angle equals an interior opposite angle there. Or this exterior angle equals that one there. I wouldn't go for this one because it's right out in the middle of the sticks and we don't know anything it's equal to other than the vertically opposite angle. So if I went that way, I would go for R3 equal to Q3 and 4. R1, the R3, yes. R3 equals Q3 and 4. But anyway, the other one is converse of angles in same segment. But we don't have any bow ties there. We need that joined across there. If this angle was equal to that angle, then it would make it a cyclic quad. So I'm going to go and say, well, R3 would equal Q3 and 4 by exterior angle cyclic quad. So let's prove this. Let's prove R3 equal to Q3 and 4 because that would make that cyclic. So once again, if proving two angles equal, take one and find what it is equal to. Let's take R3. What is R3 equal to? Well, it's equal to Q1 and 2, angles in same segment. Now that boils down to saying, well, is Q1 and 2 equal to Q3 and 4? That's what we need to prove. Well, remember, we've already got one body. Well, Q1 equals Q3. So all we need to do is prove Q2 equals Q4. Well, Q1 equals Q3. That's proven. Remember, angles subtended by equal chords. And Q2 is equal to S, which is equal to Q4. And there's some big hints for you. The blue shading shows you a tangent, a circle, a chord, and an angle in the alternate segment. There we are, angle in the alternate segment. Q4 equals S. The green lines show a Z. In other words, these parallel lines with the alternate angles, and that's why Q2 equals S. So let's prove this. Q1 equals Q3. Proven. Q2 equals S. Q2 equals S. Alternate angles, state the parallel lines. Q4 equals S. Tan chord, angle and alternate segment theorem. Which means, therefore, Q2 equals Q4. Now have a look what I have. Q1 equals Q3, red, pink. Q2 equals Q4, red, pink. Well, therefore, these two added will give those two added. But R3 equals Q1 and 2. R3 equals Q1 and 2. Therefore, R3 is equal to Q3 and 4. And we have completed. We now have a cyclic quad by Converse, exterior angle cyclic quad.